Let us continue resonance. In the resonance, let us take benzene. In the benzene formula, molecular formula C6H6, all the carbon atoms and hydrogen atoms are in one plane. In the benzene, all the carbon atoms and hydrogen atoms are in one plane. So we will write all the 6 carbon atoms are in a cyclic form. So we will write that cyclic form, we will write like this. And each carbon has one nitrogen. Each carbon has one nitrogen atom. Set. Now all these sigma bonds present in one plane. All the carbon atoms and all the hydrogen atoms are present in one plane. So we can give this like this also. Like this also we can give. Then each carbon, for each carbon valence is 4. That means here 3 bonds are there, remaining 1 is there. That remaining 1 electron present in the p orbital. So this carbon, this is in one plane. That p orbital is perpendicular to this plane. One lobe is above this plane, another lobe is below this plane. Okay, that means we can say all the carbon atoms, and all the hydrogen atoms are present in a plane of screen. In a plane of screen, we'll say present in a plane of screen. Okay. Now carbon undergoes what hybridization, that we'll see. For this carbon, what is the electronic configuration? Means helium 2s2 2p2. Now this carbon is having 3 sigma bonds, therefore it is providing 3 hybrid orbitals for bonding. So 3 orbitals from carbon undergoing intermixing. So one is 2s orbital, one 2s orbital plus 2 2p orbitals, plus 2 2p orbitals undergo intermixing. Therefore what we are getting means 3 sp2 hybrid orbitals we are getting. 3 sp2 hybrid orbitals we are getting. Sorry. That 3 sp2 hybrid orbitals we will write like this. Okay. Each hybrid orbital is forming bond with one nitrogen and this carbon like this. Okay. So in this carbon, the valence shell contains 3 2p orbitals. Out of 3, 2 2p orbitals have gone for intermixing. Remaining 1 2p orbital will be there. That 2p orbital contains 1 electron. Okay. This is pure 2p orbital. Now in this benzene, each carbon provides one 2p orbital containing unpaired electron, Okay, each carbon provides one 2p orbital which is perpendicular to the plane, plane means screen, which is perpendicular to the plane. Sorry. And how they are there? They are parallel to each other, like this will be present. They are parallel to each other. Sorry. The 6 carbon atoms, here 6 carbon atoms forming a cyclic ring, that is a cyclohexane ring. Okay. So now 6 carbon atoms forming like this ring. 6 carbon atoms formed like this ring. This is this corner means one carbon. This corner means one carbon. This carbon is providing one 2p orbital which is perpendicular to this screen plane. That means this lobe is above the screen, this lobe is below the screen, like this is there. Then this carbon is providing one 2p orbital which is perpendicular to the plane. So each carbon provides one 2p orbital. Each carbon is providing one 2p orbital. Then each 2p orbital contains one electron. Each 2p orbital contains one unpaired electron. Now 2p orbitals these 2p orbitals are perpendicular to the screen, perpendicular to the molecular plane screen, but they are parallel. Therefore, this p orbital is overlapping with this p orbital laterally. Lateral overlapping is possible. Then this p orbital is overlapping with this p orbital laterally, like this possible. Then these two p orbitals undergo lateral overlapping. Therefore, we got what in the sense. Now we will say here 6 carbon atoms we are writing, and pi bonds. Here one pi bond, that pi bond will write. Here one pi bond, that will write. Here one pi bond, that will write. Okay. This is the structure proposed by which in the sense Kekule. Kekule proposed this structure. So as per Kekule, the benzene structure is this one. In benzene, 3 pi bonds are present. As per Kekule, the benzene has 3 pi bonds. Then we will go for electron shift. If this pi bond shift to this place, then this pi bond will shift to this place. This pi bond will shift to this place. This is called electron shift, is called resonance. So we will get a resonance structure. We'll get now another one. We'll see. Now what happened means pi bond shifting. So this pi bond is shifting to this place. This pi bond is shifting to this place. Sir, this pi bond is shifting to this place. So we are writing pi bond here. This pi bond is shifting to this place. So we are writing pi bond like this. So these are resonance structures. Resonance structures are separated by double-headed arrow mark. This is proposed by what in the sense Kekule. Then Dewar also proposing structure for benzene. How that structure is there, that we'll see. 6 carbon atoms in a cyclic ring. Then he gives one pi bond here, one pi bond here. Then these two carbon atoms are connected like this. This carbon atom or this carbon atom and opposite carbon atom are connected by a bond like this. Like this structure proposed by which scientist in the sense Dewar for benzene. Now what we will do in the sense, what is another structure proposed by Dewar that we will see. Another structure proposed by Dewar is like this. Here pi bond, here pi bond, opposite carbons are linked by a bond like this. Then another structure proposed by Dewar that we will see here. Here pi bond, here pi bond, and these two carbons are linked like this. Okay. Next structure proposed is now Dewar. Next structure proposed by Dewar is like this. Okay. So Dewar is how Dewar proposing the structure that we will see. How the Dewar is proposing the structure that we will see. That is 6 carbon atoms we will write like this. And each carbon atom is providing 2p orbital for 2p orbital which is perpendicular to the molecular plane, which is perpendicular to this. So each 2p orbital is having one unpaired electron. Now how the bonding takes place that we see. Now Dewar says that this 2p orbital and this 2p orbital is making a bond. So two 2p orbitals making a bond like this. Then this 2p orbital and this 2p orbital is making a bond that is like this. Then this 2p orbital and this 2p orbital is making a bond that is like this. In this way Dewar proposing. Sir. So these we will write it as a double-headed arrow mark. We will separate them by double-headed arrow mark. Sir. We are separating them by double-headed arrow mark in the sense we can interconvert, isn't it? That means a short electron shift takes place, therefore interconversion is possible. That is the meaning. Sir, is it correct or wrong? We'll see. Now we'll say we'll take this benzene cyclic ring. Now each carbon is providing 2p orbital. So one 2p orbital, second 2p orbital, third 2p orbital, fourth 2p orbital, next 2p orbital, next 2p orbital. Here 2p orbital, here 2p orbital. Each 2p orbital contains one unpaired electron. Each 2p orbital contains one unpaired electron. So how the bonding is possible as per D1? These two p orbitals undergo lateral overlapping. So it gives pi bond here. These two p orbitals undergo lateral overlapping. This gives pi bond here. These two p orbitals undergo lateral overlapping. This gives bond here. Okay. Sir. Now electron shift we will see. We will see about electron shift. How the electron shift is taking place, that we will see. How the electron shift takes place. Now what happens means, it is making bond. It is making bond like this. While this is making bond like this. While this is making bond like this. So how the electron shift is there, you see. So when this bond is migrating here, this bond is migrating here, this bond is migrating here. So we will get this. So we are getting this. So that we can separate them by double-headed arrow mark. Sir, can we separate? Can we separate them by double-headed arrow mark or not? We'll see. It is Kekele proposed structure. It is a Dewar proposed structure. Kekele structure and Dewar structure. Shall we? Can they be interconverted or cannot be interconverted? That we'll see. Now, this Kekele structure will take. Here one p orbital will take. P orbitals we are taking. Okay. Now we will give pi bond. Here overlapping. This gives pi bond here. Here overlapping takes place. This gives pi bond here. Here overlapping is possible. This gives pi bond here. Okay. Now we will go for this into d1. This into d1. How to go? Now this pi bond as it is. Next what happens means. Next what happens you see. This is this one and this one is undergoing overlapping. This one and this one undergoing overlapping. Okay. These two undergoing overlapping, therefore we are getting pi bond. These two undergoing overlapping, therefore we are getting this bond. Therefore these two also can be interconverted by electron shift. So this is the structure proposed by Kekule for benzene. These are the structures proposed by Dewar for explaining benzene. Sir, now we will see experimental fact. We will see. The experiment says that benzene, in benzene, carbon, all the carbon bonds, all the carbon bonds have same nature. All the carbon bonds have same nature. And as only one cc bond length, only one cc bond length. In benzene, all the carbon bonds have same nature and as only one cc bond length. Sir, now we will see, we will take this Kekule structure. Here, between these two carbon atoms, between this carbon and this carbon, double bond is there. Between this carbon and this carbon, single bond is present. So, as per Kekulé structure, between carbon atoms here, double bond. Between carbon atoms here, single bond. Therefore, two types of bonds. Therefore, this Kekulé structure is unable to explain this experimental fact. Therefore, this is not a actual structure of benzene. Sorry. Now, D-word structure will take. In the D-word structure, between this carbon and this carbon, double bond is there. Between this carbon and this carbon, single bond is there. Between this carbon and this carbon, higher length single bond is there. Between this carbon and this carbon, higher length single bond is there. So as per DVAR, how many CC bond lengths possible means 3 CC bond lengths possible, but experiment says only 1 CC bond length, and also all the CC bonds have same nature. So DVAR structure is also not explaining about this benzene structure. So we'll see regarding this. In this one, if you see, between this carbon and this carbon, single bond is present. Between this carbon and this carbon, a long single bond is present. Therefore, all the carbon-carbon bonds are not having same nature. Therefore, all the carbon-carbon bond lengths are not same here. So, then these structures are not actual structures of benzene. These structures do not explain experimental fact about benzene. So then what is the actual structure of benzene? For which what we will do in the sense, we'll take these structures, we'll take. From these structures, let us try for actual structure of benzene. In all these structures, what is possible means cyclohexane ring is possible. In all cases, carbon atoms present in a hexane form. In all the cases, carbon atoms present in a cyclic form. So we will take cyclic form. In all the cases, carbon atoms present in a cyclic form. Therefore, we will take cyclic form. Okay. For writing actual structure. Okay. In all the cases, carbon atoms present in a cyclic form. So we have written cyclic form. In all the cases, each carbon has one nitrogen. So one nitrogen will write. Each carbon has one nitrogen. That nitrogen we have written. So in all the cases, in all these cases, each carbon is providing one 2p orbital which is perpendicular to the molecular plane, which is perpendicular to the screen, and has one unpaired electron. So now we will take each carbon is having one 2p orbital. Each carbon is having one 2p orbital. Each 2p orbital is having one unpaired electron. Each 2p orbital is having one unpaired electron. So now let us consider that this is A, this is B. Okay, carbon A, carbon B, that we will take here. This bond, for this bond length we will take. For this bond length we will take. Then carbon C we will consider now. Carbon C. Now we are considering carbon B, carbon C. We will take this bond length. This bond length. Experiment says they are equal. Experiment says they are equal. That means here also this bond length is equal to this bond length. All the CC bond lengths have equal bond length. All the CC bonds have same nature. All the CC bonds have same bond strength. It is experimental fact. That means Distance between these two carbon atoms and these two carbon atoms are same. Therefore, this p orbital is overlapping with this p orbital laterally. This p orbital above lobe and this p orbital above lobe overlap laterally. This p orbital down lobe, this p orbital down lobe overlap laterally. Simultaneously, this p orbital above lobe is overlapping laterally with this p orbital above lobe. This p orbital below lobe is overlapping laterally with a p orbital below lobe. Simultaneously takes place to its extent. Therefore, now b carbon 2p orbital overlap laterally with a carbon 2p orbital and C carbon 2p orbital simultaneously and to same extent overlapping. Therefore, this 2p orbital is overlapping with this 2p orbital as well as this 2p orbital simultaneously and also to same extent of lateral overlapping. Therefore, to what extent pi bond is formed here? To that extent pi bond is formed. Okay, then this 2p orbital is overlapping laterally with this 2p orbital. Then this 2p orbital is overlapping laterally with this 2p orbital. Then this 2p orbital is overlapping laterally with this 2p orbital. Next, here also lateral overlapping possible. Like this lateral overlapping possible. Okay. So how how this pi bond is there means now this pi bond how it is present, whether it is localized or delocalized. This pi electron cloud is localized or delocalized. What is meant by localized and delocalized? Localized means what? Delocalized means what? That we will see. Now I will take one compound, that is this compound I will take. Here 3 hydrogen atoms present. This is one carbon, it is having one hydrogen. This is one carbon, it is having two hydrogens. Now I will take this carbon is having one 2p orbital having unpaired electron. This carbon is having one 2p orbital having unpaired electron. These two 2p orbitals are undergoing lateral overlapping, therefore pi bond is produced. Now let us take, this is carbon number 1, this is carbon number 2, this is carbon number 3. Now we can say this pi bond is present between carbon 1 and carbon 2, but not with carbon 3. That means we can say this pi bond present particularly between carbon 1 and carbon 2. Therefore, this pi bond is called localized bond. Localized means that pi bond present between particularly two carbons. This pi bond exactly present between carbon 1 and carbon 2 but not with carbon 3. Therefore, this pi bond is called localized pi bond. Now let us go for this. Now this pi bond is present between which carbons? Between A and B or B and C or both? So can you say that here pi bond is possible between particularly A and B or B and C or both? then will you say here pi bond is localized or not localized? What do you say? Think it. Now, here this structure, if you see, here pi bond is present. Now we will give numbering: one, first carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon, like this we will say. Here pi bond is present exactly between 1 and 2. Here between 2 and 3 pi bond is not present. Between 3 and 4 pi bond is present. But as per this structure, can you say that between A and B pi bond is present, between B and C pi bond is not present? Can you say? No, because this p orbital is overlapping laterally with this p orbital as well as this p orbital simultaneously and also to same extent. Therefore, how this pi bond will be present? Is it localized or not localized? How do we say? That we'll see. Now we'll take regarding that benzene pi bond we have to discuss. Now carbon atoms we have written. Then we'll go for p orbitals. Here 2p orbitals we'll write. 2p orbitals we have written. Now we will go for pi bonding. Okay. Now this is having one unpaired electron. It is having one unpaired electron. It is having one unpaired electron. It is undergoing lateral overlapping with this as well as this. That means this p orbital has gone for lateral overlapping with this as well as this, in the sense it is not making pi bond particularly with this p orbital. It is making pi bond with this p orbital as well as this p orbital, in the sense it is not making particularly with particular p orbital pi bonding. It is not making pi bond with particular p orbital. Therefore, can we say this pi bond is localized? Then this p orbital is making lateral overlapping with this p orbital as well as this p orbital. So this p orbital is making pi bond between this p orbital as well as this p orbital. So it is not making pi bond with particularly one p orbital. Therefore, can we say this pi bond is localized? Think it. So how this pi electron cloud is there means, okay, this pi bonds in the sense 3 pi bonds. 3 pi bonds in the sense 6 pi electrons. How these 6 pi electrons present? 6 pi electrons present above and below the molecular plane, or plane of the screen, and equally distributed to all the carbons, Therefore, the pi electron cloud we will represent as a ring. Therefore, 6 pi electron cloud we are representing as a ring. So now you say that this 6 pi electron cloud, it is electron cloud in the sense to all the carbons, pi electron cloud is distributed. Then can we say it is localized? Can we say that pi bond is present exactly between 1 and 2 carbons? No. Therefore, we can say this pi electron cloud is delocalized, we can say. Delocalized means not localized, not particularly between two carbons. So this pi electron cloud we have to say as delocalized pi electron cloud. So how to represent this delocalized pi electron cloud we will see. Now 6 carbon atoms we have written like this. Now the delocalized pi electron cloud, how it is present means here of pi bond, 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 here of pi bond. How pi electron cloud distributed have you seen? So here of pi bond is there, here of pi bond is there, here of pi bond is there like this. So now between this carbon and this carbon one sigma bond is there, of pi bond is there. Between this carbon and this carbon one sigma bond is there, of pi bond is there. Therefore, these two carbons, the bond between these two carbons and bond between these two carbons have same nature. Therefore, this carbon-carbon bond length, this carbon-carbon bond length is same. Therefore, this structure is explaining the experimental fact about benzene. Therefore, it is called a resonance hybrid. These are called resonance structures. These are called resonance structures. So now we have given resonance hybrid we have given and resonance structures we have given. So what about the energy of these? That we will see. Now here pi electron cloud is uniformly distributed throughout all the carbons. So all the carbon nuclei is attracting the 6 pi electron cloud. Therefore, how the attraction will be there here, you think it. Here if you see, this pi bond is attracted by these two carbons only. But these two carbons is not having pi bond, therefore how the attraction will be there, you think. Here 6 pi electrons is distributed equally to all the carbons, therefore all the carbon nuclei attracts 6 pi electron cloud. But here these two carbons attract this pi electron cloud, whereas these two carbons having not having pi electron cloud. Therefore, here attractive force in this molecule is less, attractive force in this molecule is more. Therefore, this energy is less, this energy is more. Okay, so what we are saying in the sense, this Kekulé structure, Kekulé structure is having less attraction, therefore energy is more. Resonance hybrid is having more attraction, therefore energy is less. Okay, so resonance hybrid is having lesser energy, Kekulé structure is having more energy. Okay, next we will see D-Watt structure. In this D-Watt structure, between these two carbons are far away. Therefore, this bond length is higher. Therefore, this bond is having lesser strength. Lesser strength means stability is lesser, attraction is lesser, energy is higher. Therefore, this D-Watt structure energy will be more when compared to this Kekulé structure. Sir. So we are saying D-Watt structure energy is still more, like that we say. Sorry. Next we will take this one. We will take in this D-Watt structure no pi bonds at all. This bond is more length. This bond has more length. This bond has more length. All the three bonds have higher length. That means distance between these two carbons is much high. Here also these two carbons are having higher distance. These two carbons are having higher distance. Distance is high, attraction is low, energy will be high. Therefore, this structure, this D-Watt structure is having much energy, we can say. Therefore, now we will take it is A, this is B, it is C we will take. This C is having much energy, we can say. C is having much energy. Now, we will take a energy level diagram we will take. Here energy if we take first resonance hybrid we can take. Then Kekulé structure is having somewhat higher energy. D-Watt structure is having still higher energy. In D-war structure, this structure is having much energy, much higher energy. Sir. Now, these are resonance structures. In these resonance structures, most stable form is Kekulé structure. So, most stable resonance structure we have taken. Most stable resonance structure. It is resonance hybrid. Now, we will go for energy difference between most stable resonance structure and resonance hybrid is called resonance energy. Is called resonance energy. So, what is called resonance energy? It is the energy difference between resonance hybrid and most stable resonance structure. That is called resonance energy. Now you say, if resonance energy is high, if resonance energy is high, how the stability of molecule will be there? How the stability of molecule will be there? Okay. Resonance energy is higher means these two levels are separated by higher distance. That means this resonance hybrid goes much lower than this most stable resonance structure. Resonance hybrid goes much lower in the sense its energy is much lower. Its energy is much lower means its stability is much higher. Okay, therefore resonance energy is higher means stability of the species also higher, we can say. Sir, so this is about resonance. Okay. Next, we will take about in resonance. What are the points we have discussed? That cumulative points we will see. One point is called resonance structure. Resonance structure. Another name is what in the sense contributing structures. Resonance structure. Another name is contributing structures. Another name is canonical structures. Canonical structures. Another name is alternating structures. Alternating structures. Alternating structures. These are called possible Lewis structures. These are called possible Lewis structures. These possible Lewis structures are not true structures. They are false structures. They are false structures. They are not explaining experimental fact. So, next we will see resonance hybrid. Resonance hybrid is the actual structure of a molecule. Actual structure of a molecule. Whereas resonance structures are not actual structure of a molecule. Then what is the necessity of resonance structure? Using resonance structures only we are writing resonance hybrid. Sorry. Next. Resonance structures are separated by double-headed arrow mark because we can interconvert them by short electron shifts. So resonance structures are separated by double-headed arrow mark. Okay. Next, if resonance hybrid, energy of resonance hybrid, energy of resonance hybrid is always lesser than energy of resonance structures. Energy of resonance structures. Next, the resonance energy is equal to energy of resonance hybrid, energy of resonance hybrid minus energy of most stable resonance structure. Most stable resonance structure. Next point, resonance energy is higher in the sense stability of a molecule is higher. Stability of a molecule is higher. Okay, this is about resonance. Okay, the resonance is introduced in the valence bond theory. So, in the valence bond theory, how many theories are there? Means one is pure orbital overlapping concept. Next one is hybridization. Next one is resonance. These are introduced